to this, I can see, yeah, to this 33rd Flow Talk, and one of the first, not the first, one of the first this year. We have amazing speaker, one of the co-organizers of Flow, Dan Alistarh, who agreed to give a talk. He's an assistant professor at IST Austria. He's an expert in systems, machine learning systems, in distributed machine learning. And he's recently very well known for his work on sparsification of models and algorithms. QSGD is one very highly cited work of his, and he has lots of other stuff going on. And today he'll talk about decentralized SGD with asynchronous, local, and quantized updates. I did not say what Flow is, but by now you know. So this is an online seminar in federated learning. We try to cover the whole breadth of federated learning, including algorithms, systems, optimization, cryptography, anything that intersects with federated learning. So there's some mechanism that maybe Samuel will mention. I don't know, Dan, do you like to be interrupted? Do you want questions to arise?
So I'll have some kind of natural points in my talk where I go, like essentially I go from the low level to the high level, and then I'll maybe for each one of those points I'll stop, and then we can take questions from the chat box or like people raising their hand.
So you just request, okay, excellent. And I don't know whether we still need to repeat about this raise hand feature in Zoom, so maybe we do not have to, but you could raise your hand, you could write a question into comment. We try to unmute people as much as possible so that we hear some other voices as well. That's always appreciated. Okay, so without further ado, Dan, go ahead, stage is yours.
Yeah, so thanks a lot for the introduction. So today I'd like to talk a bit about like a slightly different approach to the large-scale distributed learning that we kind of always see or we often see in Flow. So in particular, essentially the project started from our question of like, can you run these types of large-scale learning mechanisms at really large scale? And hopefully I'll give you an answer or sort of a hint for an answer by the end of the talk. So this is joint work with a large part of my lab. So Georgi Nadiradze, my PhD student, is the main author, and then also Morshtaba Sabur, Ilya Markov, Peter Davis, and Shigangli also contributed. So I guess it's always a good idea to sort of explain the title whenever you do a talk. So that's what I'm going to spend the first couple of slides on. So I'm going to start from something that I hope is familiar to pretty much all of you, which is kind of the basic federated learning setting where we have this central server, which is kind of holding on to our like global information in the form of models, for instance. And then we have these clients, which are kind of mobile devices, which could be like endpoint devices like laptops or phones, each of which has some local data distribution. So essentially, samples like photos or snippets of text and so on. And they're also able to sort of hold on to local models, which they may be able to train or perform inference on. And also notice that these distributions are kind of heterogeneous and they can sort of change over time. So they're also dynamic. So this is a setting that's really becoming very prevalent. So I think a lot of like the large companies, in particular phone manufacturers, are really jumping on this trend. And we also, I mean, we've also, as you probably have seen as part of Flow, there's a lot of stuff we already know about it. So we have efficient algorithms, and we're working on even more efficient algorithms on enabling kind of efficient learning from data in this kind of setup, right? And here I would kind of like to recommend like the recent, like the excellent recent survey, which appeared on this topic by kind of a number of authors. So in particular, like we kind of understand the learning dynamics, but we also right now know kind of how to make this more efficient or how to make this more robust with respect to various components. So in particular, we know how to deal with data heterogeneity. And if you were paying attention in Flow, you might have seen a couple of talks on this. Local steps, we now have like better analyses for the convergence of federated averaging or local SGD or these types of algorithms. And then we also know how to quantize. So we can reduce essentially the cost of transmitting over these channels between clients and the server. And then if you were kind of online last week, you could also see Hamid Hassani talking about how to deal with stragglers, client asynchrony, churn, and so on and so forth. So these are all reasonable questions when you try to deploy such a system in practice. And for this kind of centralized setting, we already have pretty good answers, right? However, I think it's always good to keep in mind the fact that, we don't, or at least ask the question, do we actually need this centralized authority? Like, are we gaining anything fundamental because of this? Or, is this kind of loss of privacy, which is in some sense inherent if you have a central authority who's kind of sort of keeping everything, can keep everything in one place? Is this kind of inherent if we want to do efficient learning? Okay, and so a reasonable question, which kind of got us started on this path, is there any way we could sort of compensate for this authority, and how much are we actually going to lose if we don't allow such a central server to exist? Okay, so this is the kind of backdrop. I'm gonna first try to give you like a rough model for the setting I'm going to consider, and then we're gonna maybe go a bit deeper whenever I present the algorithms. So this idea of doing learning in a decentralized setting is certainly not new. So I think the first paper I know of is by Tsiklis in 1984, so that's already a long time ago. And then this was sort of taken up in the sort of decision control literature, and there's kind of a rich line of work on that as well. And then I think in the machine learning, kind of large scale machine learning setup, this was popularized by an early paper by Zhi Lu's group, in particular, like Xiangru Lian, who has a couple of very good papers on this. So basically, the setting we're going to consider is kind of inspired by these works, but it's going to be, I think, extremely decentralized. So it's going to be slightly more general than I think, at least what is considered in this latter paper. And I'm going to detail that in a minute. So what we assume is that we are going to assume a regular graph G. So each node is going to have the same number of neighbors. This models most sort of networks which you have in these kind of overlays for a peer-to-peer communication, or in supercomputing or cloud computing networks. They basically have this property. So each node, we're going to assume that each node can keep sort of track of its own model, and then it has a local data distribution DI, which enable, like these two things enable it to essentially examine its loss or cost and compute gradients of this with respect to its local model. So essentially it can make sort of first order local improvements with respect to this loss function based on new data that it sees. Okay, and then so this is what nodes could sort of do by themselves. And notice that nothing really is forcing them to communicate unless they want to have like a more global notion of convergence. Each one of them could just do SGD locally, and nothing's kind of preventing that. But notice that obviously they would sort of get better results if they actually are able to communicate. So, or they're willing to communicate. So for this, we're going to only enable sort of these pairwise steps. So essentially, we're going to assume this kind of huge soup of agents, and every now and then two of them kind of meet, and they can exchange some information, and then they go on their merry ways. So basically, we're like in every step, I'm going to activate an edge which is chosen uniformly at random, and the nodes at the endpoints of this edge will take a local gradient step or some number of gradient steps. They're going to essentially take some optimization steps, and then they're going to average their models. So this is the kind of standard pattern that one tries to work with in this decentralized setting. Okay, so this is like the model itself is extremely general. I think it kind of appeared, it was kind of discovered and rediscovered a bunch of times. I would cite two papers here, Xiao and Boyd, who worked on this model from the continuous time perspective for asynchronous gossip. And then I think pretty much at the same time, this was proposed as a population model, which is very, very popular in distributed computing. Okay, so maybe one thing that I would mention is that we're going to come back to this is essentially that, I mean, we're essentially going to analyze things kind of interaction by interaction. But notice that these interactions can happen in parallel. In particular, about order n interactions will happen in one unit of time because there's just inherent parallelism in the model. So you should always, in terms of wall clock time, you should always maybe divide t by n. But I'm also going to do that for you to sort of simplify things. So, all right. So, I mean, the fundamental questions here, which are kind of the usual questions we ask, are how does does this kind of thing still converge, and how does the convergence depend on the graph structure? And then the other question is like, can this be rendered practical to the same extent that we have rendered kind of these federated learning approaches practical? So basically, we would like to see if this this supports local steps or asynchrony or quantization. Okay, so yeah, I think I have a question, so I'm gonna maybe. Right. Oh, okay. Sorry, I don't think that's a question for me. So, all right. So, so I'm gonna start by just doing a very rough sort of overview of what is known. So this topic has a long history. So basically, as I said, like there's the first paper which is of this flavor appeared in 1984. So obviously, my survey here will be sort of selective and biased. So I apologize for those of to those of you whose work I'm skipping. But basically, I think I'm mostly going to focus on the work which essentially looks at this type of optimization in the context of sort of deep neural nets. So here, I think one of the first papers was a NeurIPS 17 paper, which essentially considered a similar setting, but with essentially in these global rounds in which pairs of essentially agents are matched according to some essentially matching matrix, and then there's one global step which allows each agent to communicate with a neighbor or with a bunch of neighbors and update their information, right? So then they focused on the non-convex case, and like very interestingly, they were able to show under quite a few assumptions that you can get square root of n speed up. So essentially, the best speed up you could get in the like for SGD in the non-convex case. And however, I mean, there's one kind of important limitation, which I'm going to discuss quite a bit in this talk, which is like they required a lot of steps for this to happen. So basically, they show that there's this kind of mixing process, and then this process has to go on for a long time in order for convergence to be achieved. So for instance, like this number of steps is quite huge if you have a lot of nodes. So then there was there were a lot of additional, there was some additional work on relaxing kind of synchronization and communication assumptions for this type of work, which is, I think, was performed roughly by the same group or the same loose group of co-authors. So they essentially proposed a version which allows for sort of non-blocking or asynchronous synchronization, which has this similar guarantees. And then they also came up with a version which allows for quantization. Although here, there's this quite heavy memory requirement, which says that practically every node will have to have keep an extra buffer, like an extra copy of the model for each neighbor. So that's which I think would be quite difficult to do in a very large scale setting where you could meet pretty much anyone. So yeah, and then there was a paper, I think, out of like Facebook research, where they proposed a different version of such an asynchronous algorithm, which allows sort of the asynchronous pushing of the gradient. So it's kind of a technical change in the way communication is done, but which actually enables quite a lot of speed up in practice. And but however, their analysis required fairly strong assumptions. So I think they require t greater or equal square root of d times n, where d is actually the model dimension. So for neural nets, this would be pretty large. So yeah, and then there's a lot of interesting work in the, I think in the past couple of years on essentially analyzing versions of this and trying to get like the right bounds in the convex and sometimes in the non-convex case. So Wang and Joshi, I think, were the first. And then Anastasia Koloskova from VFL has like a long line of very interesting work on this, where essentially they provide very good bounds of sometimes in the convex case and then extend it into non-convex one. However, I think all of this work assumes this kind of global kind of synchronized model of computation where you have like each agent interacts in each round. Okay, which is slightly less general than what we're doing. So, and then there's this very recent paper, which is, I think appears in AI Stats by Peter's group, I think in a collaboration with EPFL, where they essentially look at stochastic quantization and variance reduction. So yeah, so I think that I'm gonna try to wrap up the sort of the detailed sort of related work, and I'm gonna maybe try to come up, like give you kind of a large high level view of what we know and what we don't know. So what we know is that these algorithms converge and they can outperform centralized ones in certain settings, in particular where all-to-all communication is expensive or impossible. However, in particular for the example of neural nets, which we kind of care about, these require a lot of more gradient steps to converge to the same level of accuracy. So we can also sort of reduce the communication cost by analyzing asynchrony, local steps, and quantization, but all of these things have been kind of applied separately. So each paper in some sense, like usually just focuses on one type of relaxation and tries to get good bounds for it. However, we don't know whether all of these techniques can be applied in conjunction, whereas in the centralized case, we kind of know that this is the case. And then the other thing that we'd like to know is whether, like, is there anything kind of inherent about this extra number of steps which seems to be needed for convergence? And then the other thing is, like, can we beat state-of-the-art centralized variants like a large batch SGD? So can this really be practical? Okay, so that's kind of the context for this work. I'll try to see if there's any questions here. Sorry.
There's one question. I'll try to unmute Marco.
Yeah, so I can read the question. So basically, the question is whether essentially this extra number of steps is true both in theory and in practice. So basically, I mean, all of the known analyses require like this t greater some polynomial factor in n, which is kind of, I don't think is sort of realistic. So basically, I don't think that their experimental sections actually match this because they would have to run for a long time, essentially. And then the other thing is that, yes, I mean, in practice, if you follow the SGP paper, like in the SGP paper, they essentially run, I think, for 3 times more epochs than the SGD baseline in order to reach the same level of accuracy. And I think in ADP SGD, they actually, they admit to not being able to reach, I mean, they run for exactly the same number of epochs, but they don't reach the same level of accuracy. And we've done some additional testing, and we noticed that, I mean, these methods, if you run, even ADP SGD, if you run it for longer, then it will kind of eventually recover, even though sometimes this can be very, very long. And so, I mean, there was kind of a limit to how long we actually tried to see this. But yes, I think this would, I think this is certainly something that appears to hold both in theory and in practice.
Thank you, Dan.
Yes,
for neural nets.
So Marco, I heard you now. So I'd like us to be unmuting people if we can, so that we can actually hear some interaction rather than reading, if possible. So Marco, if you have any follow-up questions, go ahead and just ask in person.
Hey, Marco is muted.
He was unmuted just a second ago. I heard him saying something.
I cannot unmute myself. Samuel is, controlling. But,
okay.
Yeah, thanks for the answer. Then that's so far that's the question, and you answered to my satisfaction. So thank you.
All right. I mean, I'm going to actually come back to this and give some specific examples in the experimental section. Maybe hopefully I can get there in time. So, all right, good. So what do we do? What do we do in this work? We essentially give an algorithm which allows for all of these things to work in conjunction. So basically, you can do local steps, asynchronous communication, quantized updates. And we show that the resulting algorithm from the technical perspective scales in the sense that its communication cost essentially becomes a constant, which doesn't really depend on however many like nodes you have in the system, which is not a characteristic of other algorithms. And then I think that the main contribution is actually the analysis technique, which uses a new connection to multidimensional load balancing processes. And this allows us in particular to reduce the number of interactions needed to show convergence for these algorithms to t greater n fourth. I mean, we don't know if this is tight, but at least this is something that actually are real runs in practice on ImageNet or like WMT. They actually that actually hold. So basically, there's like the guarantees actually sort of transport from theory to practice. And then we implemented the algorithm in PyTorch and TensorFlow, and we showed that it does sort of outperform in terms of throughput the other decentralized methods, and also in terms of accuracy to some extent. And then we also show that sometimes for certain model combinations, it actually can outperform large batch SGD. So this is basically what you're going to see for the rest of the talk. So let me start by kind of explaining what the process looks like. So basically, we have this population of n nodes. I explained that they're going to communicate in pairs. So the first, like the V1, is really sort of pretty much an instantiation of what I tried to explain before. So basically, each node has a model. And in each iteration, each node essentially performs some local number of steps. This H, you can think of it as fixed if you, I mean, just for simplicity, but it actually could be a random variable. So basically, they could just like run for a while, which is given by some Poisson process or something like that. So basically, we take some local number of steps, and then we look for a neighbor. Like if a neighbor hasn't contacted us yet, we're going to look for a neighbor uniformly at random and try to sort of just like connect to it and see what its local model is. Okay, so if the neighbor is still doing its local steps and is not contacted by someone else and sort of concurrently, we're going to wait for it to finish. And what we're going to do is we're going to average them all. Okay, so basically we have these two guys. They get selected at random from the population, and they just average the models. Okay, this is kind of the nice theoretical view we would like to have of sort of what I explained before. And in fact, it is kind of related to previous work, but it's not exactly the same. So in particular, with regards to this long line of work on sort of SGD for neural nets, usually they assume the pairings are global. So basically, all of the nodes, essentially, you have like connections in every round, and then you have some interaction matrix, and then you can sort of go through. And then it's pretty much the same is also true for the other work. So I think one of the kind of main differences is this fact that we sort of assume random pairings. So then what do we assume about kind of the loss function? It's kind of the usual functional assumption. So we assume unbiased local gradients. We assume kind of sort of L Lipschitz for gradients as well. And then we will work with two types of sort of gradient bounds, essentially, like, bounds for the variance of the stochastic gradient. The first type of bound, which we will need in cases where we talk about asynchronous, like fully asynchronous algorithms, which allow kind of unbounded delays, is going to be the second moment bound, which is maybe more like kind of more stronger than we would like, but it's still kind of adopted by part of the literature. And the other one which we're going to work and under which the our main result actually works is this kind of variance bound, which is kind of stronger than, it's kind of a weaker assumption than the second moment bound. So here we are going to assume that there's kind of a local bound on variance with respect to how far the local gradient can be off from the true gradient, but then also in terms of the global variation of like gradients, like local full gradients versus the ones like the full one for the sum. Okay, so we're going to also assume, like as I said, that the graph is R regular and that we have a bound on its second smallest eigenvalue. This is kind of standard in these types of analyses of, let's say, gossip processes and so on. And for instance, like if you want to think about an example, like in the case of a fully connected graph, then you would think you would have R equals N, so everyone's connected to everyone, and lambda is 1 over N. So the thing I want to maybe emphasize about this topology assumption is that this is, I mean, it doesn't mean that everyone connects to everyone in every round, just that like whenever we select an edge, we select an edge at random from this graph. So basically, if the graph is a cycle, we only have these edges to choose from, whereas if the graph is a clique, then we can choose all of the edges. We can choose pretty much any edge. Okay.
So I have a question, if I may. So this regularity,
sure.
so this regularity, where does it come from? Because in standard gossip literature, all that you need is a connected graph. So there must be some technical point where you need this.
I mean, it's actually from the technical perspective, the main reason why we haven't really, I think the algorithm, some version of the algorithm would actually work without this regularity assumption, but it just notice that, for instance, if you would have a star graph or a graph that's kind of really unbalanced in terms of number of connections per node, then for instance, the node in the middle of the star would have a much larger weight in terms of like how much its gradients are driving the optimization process. So basically, we need the regularity assumption in order to have some sort of unbiasedness with respect to the local functions. But I think this could be fixed by doing some kind of rebalancing and so on. But for this, nodes would need to know more about the structure of the graph in order to do the rebalancing of the losses. So for this, because we didn't want to go too far into this direction, we just assume sort of regularity. And here I would mention that I think, Marco can probably say more about this, but I think most supercomputing networks are regular, and also many of the networks we work with in this kind of in the cloud setting are also at least mimicking regular graphs. So I think it's a reasonable assumption to make for a certain setting.
Right, but I presume in fair learning setting, this probably wouldn't hold. But then the networks would be changing in time and so on and so forth. Anyway, but thanks for pointing to the technical point there. That answered my question.
All right, thanks. Right. So basically, what are we going to show about this? So basically, we're going to focus on this quantity, which is going to be plainly the average over local models. So, and we're going to show some convergence sort of property with respect to this average. Notice that actually, if you want to know about convergence with respect to specific models, like does the model of the specific node converge, then we should also be able to prove something like this under like for some version of the algorithm as well. So basically, the theorem says that assuming that agents interact every 8 steps in expectation, so this can be a random variable. Sorry, the number of the interaction times could be kind of random variables, and that under some settings of the learning rate and on the number of interaction steps, then we essentially get that we get this kind of ergodic convergence condition, which essentially says that essentially your gradient is going to be upper bounded by a term which depends on the sort of distance, the initial distance from the optimum, divided by h times square root of t, and then plus k times some constants which depend on the sort of problem setting. And then you're going to have a dependency on the variance times the number of local steps times some graph property over square root of t. Okay. So
I have one question. Sorry that I asked, but this seems like an unbelievable result. Are you sure there's no average on the left-hand side?
Oh yeah, sorry. I think there's a 1 over t.
Otherwise, okay.
No, this would be incorrect. Sorry, I think this is just a typo. I apologize. Yeah.
Okay.
No, it wouldn't. Certainly, this wouldn't be true. Yeah. Okay. So what does it mean? So basically, let me try to interpret this a bit. So basically, this is kind of the nice term, which gives us sort of a progress in terms of how progress in terms of number of steps times h. So in some sense, this this term sort of shows that we are getting the amount of progress that we are expecting to get, because in terms of the total sample complexity of our algorithm. And this is kind of the ugly term, which comes because of variance, right? So basically, we're essentially getting this progress term plus this variance term. Hopefully, fortunately, both of these kind of decay with t. The first thing that I would like to mention is that these, since we have n interactions happening in parallel on average, if we are measuring time from the point of view of a single local node, then we have t goes to nt, n times the local time. So then the wall clock speed up becomes square root of n, which is kind of optimal if you disregard the huge noise term. Okay. And so basically, we're happy if in a regime where the first term dominates, because we are getting the benefits, the kind of full benefits of SGD. However, we also clearly have a large cost due to decentralization. So basically, we're getting linear dependencies in the variance terms, h square, and also the graph properties. Okay, so in particular, like basically, we would like to have our graph be as connected as possible, so that we minimize this cost over here. Okay, so right, so basically, one observation is that all of these things, in some sense, make sense. So basically, we are making progress sort of at the rate of h times square root of t, but also because variance increases kind of at the rate that's sort of linear or quadratic in h, where we are also seeing this sort of blow up on this side as well. Okay, so what does the analysis look like? So basically, the naive approach would be to try to say something like, okay, these are the local models. This is kind of the optimum we're trying to get to, and then each one of them is kind of making progress on its own, and therefore, if they average, it probably will go in the right direction. Okay, unfortunately, there's a lot of messy stuff, and if you've looked at decentralized algorithms, you probably know what I'm talking about, because we now have three sources of noise. So the gradients, which are kind of fine, local steps, which we also kind of know how to deal with from like analysis of federated averaging and so on. However, one thing that's kind of new in this setting and quite annoying in the analysis is that the interaction rates are also random. So notice that since we're picking pairs uniformly at random, a single node could actually sit on the side without interacting at all for quite a lot of time. So basically, by the coupon collector process, you could have a node not interacting. And in fact, you always have a node sort of not interacting for about n log n sort of consecutive interactions, even if your graph is a clique. So this means that, unfortunately, this means that your nodes are, it's really not clear that your nodes are kind of keeping in sync, whether it's not clear that they're actually well grouped. So in particular, you could have, in theory, you could have like nodes which are sort of left behind, right? So basically, the key technical issue that we had in the analysis is bounding model variance, which we roughly like denote as this potential, essentially the difference, a norm between an individual node and sort of the mean. And kind of this needs to be bounded in order to be able to argue that the nodes converge jointly. So we model this as a highly dimensional load balancing process. In some sense, the key lemma, and we actually sort of adapt this result based on the exact setup that we're trying to analyze, is that this potential in expectation is constant with respect to number of steps t. So basically, as you're going throughout like this kind of optimization manifold, these models are actually staying sort of close to each other, and the size of this ball does not actually depend on the time. It only depends on stuff like the learning rate, learning rate, number of nodes, number of local steps, and gradient bound. I mean, I'm giving you a kind of a simple version of this bound for the version where we're assuming a gradient bound. Okay, and obviously also some graph properties. Okay. So this holds because this quantity can be shown to have supermartingale-like behavior. So if it gets too very high, then we can show almost surely it sort of starts to decrease. And then the next step is essentially, once we know that all of the nodes are roughly within a ball, then we can show that we can sort of reduce this analysis to something like noisy SGD, because like each gradient step is going to be taken with respect to something like a slightly different version of the model, but we know that these are fairly well concentrated. So this can be made to work. Okay, so yeah, this is sort of the very high level sort of intuition for the analysis. However, notice that when we actually implement this, I mean, nodes cannot really wait for each other. We would actually lose a lot of the kind of the inherent speed of the algorithm if we implemented this kind of completely blocking version. So the second version of this algorithm, which essentially tries to model what we're actually implementing, has nodes maintain local models, but also communication buffers. So basically, the node will work on its local model for a while, update it, and then periodically just push the version of that model into the communication buffer. And communication is always done without within the buffers. It's not ever done directly by reading the other guy's model. Okay, so again, the algorithm looks a bit the same, but in the first step. But then with the sort of after we're done with the local steps, we compute this kind of delta, which is the progress since the last step. Then we pick a neighbor at random. We read their version of the buffer, which essentially contains what they had before they started doing their current local steps. We average those. So basically, we average those kind of older versions of the model, and then we apply the progress onto this averaged version of the two, kind of slightly stale version of the two models, and then we also update our buffer to this. Okay, so basically, this is hopefully this sort of makes sense. It's just kind of a buffered instantiation of the previous process. So basically, instead of averaging the models, we're averaging these stale buffers. Okay, so then again with this annoying sort of, I said there's a 1 over t here, obviously. Basically, under the same set of assumptions, we're going to get pretty much the same thing here with a different constant. And for this version, we actually assume that we have a second moment bound on the gradient. So we essentially get pretty much the same result because we apply a similar version of the analysis I described before. Okay, so where are we now in terms of where we wanted to get to? So basically, we have pairwise interactions, local steps, and asynchronous communication. And we have guarantees of this type, essentially this kind of nice term, which gives us some notion of like linear, more like square root of n speedup. But for this, we're actually paying for quite a, like we're paying for this with this noise term. Notice, however, that, I mean, in some sense, this noise term is not that far from what you would get with local, for instance, with localSGD. If you follow the exact dependencies, I think, for instance, in the first analysis, at least of localSGD, this h would be like the h square is kind of you would get an h, but otherwise, I think some of these dependencies do appear to be inherent. Okay, so we're trading off noise with speed up. However, when implementing this, we notice that this is still kind of not good enough, because if the nodes are, for instance, trying to optimize transformer-like models, then they will actually need to send like hundreds of megabytes in each interaction, which is quite a lot. So it would slow down the whole thing. So basically, the next iteration tries to get rid of this. And I mean, the kind of tempting first approach is just to quantize the models using some kind of stochastic quantization and be done with it. And so imagine this sort of figure, which mimics the thing that I sort of described before. So we imagine we want to have these two models interact and average, but we want to quantize this one. And this is, so the problem here is that standard quantization schemes will actually have quantization error, which is proportional to essentially this red arrow, essentially the norm of the points. However, what we know is that the points are well concentrated, but their norm could be very large, because I mean these I mean, the models themselves could be, I mean, they don't have to have a small norm, right? So then the standard fix in the decentralized, if we actually had this kind of federated node, would be to quantize the difference from some well-chosen reference point, which the centralized controller is giving us. However, that actually doesn't work here because we don't have such a node. Previous fixes for the decentralized case were either to maintain a certain buffer which contains the reference point for any possible neighbor, which in a large scale setting wouldn't really make sense. However, like a very clever alternative idea, which was proposed recently, was to essentially do some very like interesting version of variance reduction in order to sort of reduce, take advantage of the fact that these models are well concentrated. So here we actually take a different approach. So basically, we use a quantization scheme whose error does not depend on the norm, but whose quantization error only depends on the model variance. So basically what happens is when I quantize my node using kind of a lattice quantization technique, and I send you I send you my model, and then what you do is you take the model you receive and you decode it with respect to like as a reference point, which is in this case your own model. And what we show is that like if the lattice is properly defined, then you'll actually, your error will only depend on the variance between the nodes and not on the norm of the models themselves. Okay, so that's kind of the main trick. The observation here, and this is kind of why I kind of like this, is that basically we're again using the fact that like the gamma bound actually gives us a bound on how far the models are. So basically we're sort of bootstrapping on a property the algorithm already has. And the other thing, which is, I mean, which makes, I mean, I think I made it sound fairly simple, but this is unfortunately not simple, because the quantization itself can fail with some probability if you don't have proper bounds on the size of this ball. So for that, due to that, I mean, things actually become a bit more complicated. So, all right, so what does this third variant looks like, which actually takes the number of bits transmitted into account? So basically, we have exactly the same thing as before. Again, we compute our progress, and then we are actually going to sort of average our local model with respect to the quantized version of the model we read from our interaction partner, and push this thing to like a quantized version of this thing into the interaction partner's remote buffer. And then we're going to apply our local progress onto this. So basically, this is kind of a merge of the two, like this quantization idea and the previous sort of non-blocking progress idea. Okay, so instead of BI plus BJ, we actually are doing BI plus quantized BJ. Okay, so the theorem with this annoying bug is essentially sort of we obtain essentially the same. I mean, we actually this upper bound is exactly the same. But we can actually guarantee a dependency, I mean, a number of bits used, which is linear in t plus log t, where t is the number of steps we have run for so far. And this log t actually comes from the fact that the quantization scheme itself can fail. Okay, so all right, so back to the high level view, where are we here? So basically, we are able to sort of plug in local steps, asynchronous communication and quantization. What do we lose? We do need this t greater or equal n fourth assumptions. However, this does seem kind of inherent for this like some dependency on the number of nodes does seem inherent, or there's some kind of dependence on the mixing time does seem inherent. Then the rate itself depends on the graph properties, which also seems inherent to me. However, and we also lose sort of this dependency in the some of the parameters of the algorithm, which is poorer than what is known, for instance, for a local SGD or federated averaging, and this may well be a limitation of our analysis. Yeah, so I'm going to stop and take a question from Marco. Hello.
All right. Sorry, I cannot react because I need to be unmuted. I need to be allowed to be unmuted. I have a couple of questions here, which I'll try to express maybe interactively. So one is whether this aspect of pairwise communication is somehow, fundamental. Coming at it from a systems perspective, right? I don't see why you could enable, 3 different clients or 4 or larger groups to talk to each other. So I wonder if it is something that allows you to then analyze the algorithm and that you would not be able to analyze if you consider a larger group. But it does seem that this is ultimately having a trade-off, so it causes you to basically slow the convergence. So do you have a sense for this?
I mean, so I think, I mean, this is a question I would have rather taken at the end, to be honest, because I think there we can actually look at some graphs, and I think things would be a bit clearer. But okay. I think there are essentially 2 short answers, or I can address the question from 2 points of view. So one, I think there really are settings where you just cannot do all-to-all communication. Like if you are actually sort of deploying sort of a mesh network or something like that, there's just no way, or it would be incredibly expensive. I think you would need to essentially redo a lot of your sort of network structure in order to allow sort of all-to-all communication, or you'd have to do gossip or something like that. The other thing is, and this is something that you can actually see in the experiments, in the transformer experiments, even in this supercomputing setting, like we ran on CSCS Pisdane, which is I think top 6 or something in the world. Like, even in that case, like this network, which costs like millions of dollars, gets totally choked if it has to do all reduces on like transformer XL size models every, I don't know, few milliseconds. So basically, my point, and there, our algorithm will actually win because it can actually sort of, it allows each node to essentially directly sense to its neighbors. And then what we see is that the loss in sort of speed or like number of iterations is really negligible with respect to the huge sort of benefit you get, because you don't have to do sort of all reduces over hundreds of megabytes. But maybe this is something I would like to take at the end, because then we have to talk on real data. You mind if I go forward and talk a bit about the results?
Yeah, I wanted to just add one additional question. Sorry, if I understood correctly from your previous slide, due to the quantization, the number of communicated bits now depends on the step that you're at. So does it mean that the communication grows as a function of training time?
Yeah. So I mean, it's not this is kind of T is kind of fixed. So you do sort of decide that you're going to run for, I don't know, 100,000 steps, and then this will depend logarithmically on the number of steps that you're running for.
I see.
But I mean, this is actually usually, I mean, for all of our experiments, this factor is really negligible with respect to like D, the dimension. Like, notice that you're sending sort of order D bits. So it's like, I mean, you're sending 25 million, like order of 25 million things, and then you also have this thing which is log of 100,000 or something. So it's not exactly the same orders of magnitude, I would say.
Fair enough. Thanks.
Yeah. So if I may steal like a few seconds of time and just say something here, like an answer to Marco. So I'm not talking about Dan's algorithm, but generally about gossip algorithms, which this is based on. So gossip algorithms can work with more than just one random edge. So one can work with a huge subset, let's say, and even the whole network. and there's everything in between. You could choose a subset of edges and they could communicate and so on. So from that perspective, there shouldn't be a limitation, but of course, I do not know how this interacts with the
this algorithm, the algorithm itself and the analysis would actually work just as well. And you would, I mean, instead of this sort of r squared over lambda 2 squared, you would actually get something which depends on essentially the expansion properties of the subset which is interacting. So this would also work, of course. Yeah. But you'd need some kind of sort of collectives which are partial or something like that, right? So you'd need to be able to do all reduces are on subsets, which are kind of chosen. So I mean, I think from a technical perspective, it would be a bit more complicated.
Yeah. All right, cool.
Okay, all right. So let me show you some graphs and wrap up. So basically, we want to look at settings where all-to-all communication is expensive or impossible. So there are two settings that I know of which kind of fit. Basically, very large-scale training where you have a lot of GPU nodes. Or peer-to-peer computing, where you have hundreds of wimpy nodes for communication, but which can implement some kind of overlay. So we looked at the supercomputing setting because it makes more sense for it's fairly popular, and there we have better baselines to compare against. So basically, we have the other decentralized methods which have been tested in the same setup, and also large batch SGD, which is super tuned for the setup. So it's a very tough thing to beat. So basically, as I mentioned before, we're running on Disdain, which is Europe's top supercomputer, as far as I know. And it has, I think, up to a few thousand single GPU nodes, which are connected by really kind of the best network money can buy. And the topology actually is a regular expander, so it sort of matches our assumptions. And yeah, so it's kind of the standard setup. It's kind of one GPU per node, and we're going to do training CNNs and transform Excel. And we run the asynchronous variant, this kind of non-blocking thing, with 2 to 5 local steps. We didn't find that there was like such a big difference here, both in terms of performance and convergence. So I think we fixed it to 3 for these experiments. So actually, one thing I want to mention is that this t greater or equal n to the 4 actually holds for the number of steps we consider in this step. But t greater or equal 9 and n to the 6 would not. So, okay. So basically, the first question always is whether we can recover accuracy. And here, I think I mentioned this a bunch of times already. The algorithms do tend to need more local passes over the data set to recover full accuracy. So this is also something we can see, and this kind of comes from this noise. So, or it can be explained due to this. So basically, what we're gonna do to allow for this is we're gonna allow algorithms to run for more epochs. Essentially, we're just gonna stretch the training schedule with exactly the same hyperparameters, but run it for some multiple between 2 and like 1 and 3 or something like that. Okay, and we are going to compare against sequential SGD, large batch SGD in terms of accuracy. So this is what we get. So basically for ResNets, these would be the SGD top ones. These are the large batch SGD top ones, which we got after some tuning. And this is what we got with Swarm. So basically, we are able to recover within less than 1% relative for all of these. But notice that our multipliers are between 1.4 and I guess 2.5 essentially for these models. So essentially we have to run, at worst, we have to run 2.5 times more essentially for more time for this exact setup. So, and this is actually slightly less than what we've seen in the literature. For instance, SGP is 3x essentially, just runs sort of 3x more. And what they notice is that for some setups where the system is really bottlenecked, even though they run for more epochs, they're actually able to converge faster because their algorithm is much faster. So, okay, so how about speed? So here we compared against the other decentralized methods. And here what we're doing is for ResNet 18, we're just 0.4 seconds is kind of the per batch time. This is the computation time. And the rest is the communication time as a function of the number of nodes. So essentially we take points at different number of nodes. So our algorithm is the sort of the red line. And the obvious thing is that the red line is lower than the other lines. So that's kind of good, but that's not my point here. So my point is that the red line is actually stays flat as we increase the number of nodes. So it does seem like the communication cost appears to now be constant with respect to the total number of nodes, which is really what we want from a decentralized algorithm. We don't want it to be dependent on like hidden functions of the network, which would make it sort of increase. And okay, so from this point of view, our per batch times can be from between 2x and 3x lower than those of other methods. So what we get so far is that the algorithm is faster because it communicates less. And however, the end-to-end speedup that you would get at the end of the day would depend on how much faster this pairwise communication is relative to the all-to. Okay. However, things actually get more interesting if we look at the transformer example. So basically, for transformers, this graph shows you essentially the number of tokens per second, which is essentially raw throughput for different algorithms, essentially for a different number of nodes. So the first thing that I find interesting here is that essentially all reduced SGD, even on this like sort of top 6 supercomputer, is not actually able to do. It's just not on the chart here. It's not able to do all reduce at 64 nodes because the model is extremely large. So so basically, it's really not an option for large node count. And even relative to the other decentralized methods or local SGD with sort of 10 local steps, which we were able to make to essentially to converge, this kind of pairwise asynchronous quantized approach does seem to give you more throughput. So okay, so it seems like the transformer example could be better, or like could be sort of promising for us. So then the question is, are we actually able to recover accuracy while not running for more epochs? So, and for this, these are kind of the training time versus accuracy, this sort of accuracy versus time, for local SGD versus swarm versus the best performing previous decentralized methods on 16 nodes. So basically, the baseline accuracy here is 26.1 blue score, which would be kind of the sort of top 1 validation, if you will, correspondent in the setting. So what we noticed with our algorithm is it's able to slightly surpass the baseline, and it's able to do so about 50% faster relative to large batch SGD, which is relative to local SGD, which is would be the standard approach here. And yeah, so what's interesting is that in the context of this very highly overparameterized model, it seems like we are actually able to recover full accuracy without doing the bulk multiplication. The same is not true at 32 nodes. And so basically here we actually have to have a multiplier of 1.5, but the speed up is also larger. So we get a speed of about 70%. So, and we're also faster consistently than the previous method, just because we just communicate less often. Okay. So you can have a look at the paper for more experiments, but generally we outperform the other decentralized methods in terms of speed, because we don't compute as often or communicate as often. And the main reason is just, as I said, so basically, I would like to end on a hopeful note with respect to the performance of these decentralized methods, is because it does seem like people are moving towards these larger scale models where all-to-all communication, as you could see, is sort of hard or sort of breaks down at some point. So then it does seem like these types of methods could be competitive even in this very high performance setting. So if you I invite you to also have a look at the paper where we have experiments for a much larger number of nodes, up to 256, and you can also see sort of ablations with respect to number of local steps and so on. Okay, so all right, so thanks for hanging around for so far. So basically, the last, I want to kind of leave you with a couple of ideas or questions. So I think we have shown that this approach allows essentially to combine all of the current relaxation approaches which render algorithms practical with speedups in some regimes. then so I think we can compensate for, but not fully replace the fact that we don't have a coordinator. So basically, our methods do have higher memory costs because they have to implement buffers, and they need a higher number of iterations to mix, at least up to what we know from the theoretical point of view. So I think there's more research needed in basically further tightening these types of bounds, but also, I mean, I think it would be very, very interesting to see if this, this behavior that we noticed and also other people noticed can be removed. So basically getting sort of the like true speed up with decentralized algorithms. Okay, so so maybe a couple of avenues for further work would be to like prove that some of these things that I mentioned that seem inherent are really inherent, like these dependencies on graph structure, number of nodes, and so on. Do more tuning and see if there's learning rate schedules which are better for decentralized, and then also look at whether this can be actually deployed at massive scale. So thanks a lot for your attention, and I'm happy to take more questions if there are some.
Thank you, Dan, for this fantastic talk. Let's handle the questions by unmuting everybody, since the time is already up. They'll be more efficient. So could you, Samuel, allow everybody to unmute themselves, and then we'll just take questions as they come.
Yeah, so if you have a question, you can just unmute yourself freely. Now it's available.
All right, so I can ask one then.
Go ahead.
Experiments that you showed, they seem to be running on a supercomputer, but I saw that the number of nodes was somewhat modest, somewhat limited. I was wondering, you know, what was the furthest that you took? Right? How large?
So we have, I mean, I guess it should be said that, I mean, people are running kind of useful stuff on the supercomputer. So I mean, weather simulation, stuff like that. So there are more than 1,000 nodes, but we try not to use them all all the time. So also in some regimes, for instance, the transformer Excel example, I mean, there's some kind of a reasonable upper bound for how many nodes you want to try to deploy on this, because it just won't get speed up after a while, pretty much anything with anything you would do. But so we ran, I think if you look at the paper, we ran up to 256 nodes, and the algorithm still does converge. At some point, though, we did notice that for some, like for larger models, essentially we saw that there was bottleneck in just like there seemed to be network bottlenecks after 64 or 128 nodes, where we wouldn't, I mean, even the decentralized algorithms wouldn't scale anymore because there's probably some kind of underlying network topology we're sort of conflicting against. So there's essentially congestion on the net. So I showed, I think I focused on sort of some examples which were sort of clear or sort of simpler, but you can have a look at the paper to see more sort of results for a higher number of nodes. So as I said, I think we have up to 256, so which I think is fairly reasonable.
All right, thanks. I will look at the paper. One follow-up question to this, though, is so a supercomputer is, you know, kind of like highly regular, and DNN training also happens to be a fairly predictable operation in terms of performance. So I was wondering, you know, in practice, to what extent does the asynchronous communication that you allow actually happen, or whether you notice that, you know, ultimately most of the communication is actually done on predictable rounds?
I mean, so actually we did notice, I mean, so I think one way to actually examine this in a bit more detail is if you look at this graph, because essentially, I mean, notice DPSGD essentially does, it's kind of does synchronous. It would be similar, let's say, to the first version of the algorithm that I proposed, like I suggested, like this kind of theoretical version where you latch onto someone and you actually wait for them to sort of synchronize with you, and then you transfer models. Okay, and notice, I mean, notice this has communication cost which is at least 2x higher. And basically, the fact that you synchronously sort of copy two buffers from buffers and so on, that actually seems to be quite a large cost in terms of even per iteration. Okay, so I would say, at least as far as I would say, I think that this is actually important. So it does make sense in this regime where, I mean, like there isn't that much. Maybe we're not adding that much onto the base computation cost of the algorithm. So I think even relatively small decreases here seem to be important.
Thank you.
So we have a question from Min Tang and then Anupam. So could you, Ming Tang, could you just ask yourself so we can hear you asking it?
Hello?
Yeah.
Can you listen?
Mm-hmm. Yeah.
Okay. I have a question about your definition of the neighbor of a node.
Yeah.
So could you please elaborate on your definition of a node, a neighbor of a node? And physically, it can be a kind of distance between a node or a cluster of a machine or something.
So, I mean, okay, I guess at the logical level, what does it mean? Like essentially we create a sort of logical topology, which could be a clique or let's say a cycle. Let's talk about a cycle because that's maybe the easiest case. So basically imagine we have some nodes, they have some IDs up to 16, let's say. And then like we instantiate a sort of logical topology which says that node 1 can only talk to node 2 and node 16. Okay. So basically, whenever we sample an edge, like whenever the node sort of activates and wants to communicate to someone, these are the only two choices that it has. And then it will flip a coin to decide which one it's going to talk to.
Okay.
So the neighborhood would be 16 and 2.
Yeah. So for kind of a swarm of robot or UAV, so we can apply distance measurement for defining a neighborhood, right?
Yeah. I think so. For instance, you could do that here as well. So I think, one thing that's kind of nice about the analysis technique is that you can actually, if you have a dynamic environment, you could actually do the analysis in that dynamic environment as well. The question is, like essentially, you just have to work out what the bound in this lemma becomes, essentially what this kind of load balancing bound becomes for the exact type of graph that you're looking for.
So then I asked, the question might be directed towards, is there any mapping that you do between the logical network topology and the actual supercomputer topology and the interconnect?
Yeah, we assumed we assumed a fully connected, like essentially we didn't map onto the exact physical network here. That was kind of that's actually that was something I was very interested in, but that turned out to be technically quite difficult, because whenever you get an allocation on the supercomputer, you're actually not guaranteed to have the networks, the nodes be local. So basically, you could get all of these nodes in different parts of this huge supercomputer, and then you'd have to build. You'd have to infer some kind of topology would make sense, and that could completely change in the next allocation. So unfortunately, I think if we had, like for instance, if we ran this on our own cluster, this would have worked pretty well, but not in this setup. So yeah, but that's actually a very nice question, and that's something I wanted to do, but we just weren't able to technically because of this, I guess, trifling technical issue.
Yeah, thank you. This is very interesting work, and I think I can apply the Swarm SGD for my project. So
that's great. We do have the code available, so if you want to, pick it up, I'm very, very happy to share.
Yeah, thank you.
Okay, so Anupam.
Yes, my question is around data heterogeneity. Like, did you do some experiments on that side, and does that have correlation with your convergence?
It's a very good question. So all we did was essentially, we did play with this a bit. So basically we tried a couple of things. So basically one was the version where you have no heterogeneity, where essentially nodes can sample batches from some sort of global pool of data, which may be replicated at each node. And then what the version that I'm talking about here is actually a version which essentially where at the beginning of each epoch, each node gets like a stripe of the data. And then they're going to run their entire epoch only on that stripe of the data. Does that make sense? So basically you get a small, if there are, I don't know, 64 other nodes, you get 1/64 of ImageNet, and your epoch is only on that, okay? And then we allow for reshuffling after each epoch.
Okay, is that mentioned in the paper? I'd like to.
I would think so, yes.
Okay.
Yeah. The other version which which would be interesting to do would be a version where we essentially map the partitions initially and we never change them. But I think that would probably, that would have issues with conversion, so we'd probably have to run for longer.
Yeah, I'm just curious that the heterogeneity would have some effect on your convergence.
So what I can say is that the two versions they mentioned, these two versions I mentioned first, the version which does kind of this mapping for sort of epoch-wise, and the version which does full sampling, they don't show any difference in terms of convergence.
Okay.
Any more questions? So remember, you can unmute yourself and just ask. So maybe while we're waiting for people to ask, so did you test for sensitivity of these assumptions that you have about the variance and about the second moment, about the data similarity? So how does this affect? So we understand how it affects the theory, because these constants show up in the theory, but does this have effect in practice? Did you look at that?
So maybe I should first explain a bit the result. So the main result actually holds under sort of variance assumptions, which I think are kind of the usual ones. And then I think for asynchrony, we sort of simplified things to add this second moment bound. And the reason is actually fairly natural. So we're allowing, notice that we're allowing nodes to take local steps, and their number of local steps is a random variable. So technically, if you don't have any bound on the gradient, in theory, a node could essentially go on forever without actually taking steps. It has very low probability, but it is, there is in some sense no bound on how much the node would actually update. It's kind of, its progress could be essentially unbounded. So that's why we thought it was reasonable to add this. However, we did actually do some practical experiments to just study the difference between variance and second moment for the models that we're looking at. Essentially the variance of the gradients and second moment. And I was actually surprised that on some models, it seemed like, first of all, both of these seemed to be bounded throughout the execution. So it didn't seem like the second moment was spiking. Second moment is usually very large initially, but then it actually flattens out and is fairly regular. And I think for some runs, it actually did look like variance was larger than second moment and later in training, which is kind of a strange thing if you're from the optimization perspective, because we usually want to work under variance assumptions. But what we noticed is that actually in these cases, the variance was larger than the second moment bound itself.
So what about the compressors that you used?
So you mean like the quantization scheme?
Yes.
So basically, we only used this quantization scheme that I think Peter talked about in Flow maybe 3 months ago or something. So we use this lattice-based scheme. So the way it works is it kind of defines a lattice. You can just think of it as a cubic lattice, and then you quantize. You can think of it as quantizing stochastically with respect to a cubic lattice. And what I send you is kind of the reference point, like kind of the index of the reference point, and then all of the like the jitter, sort of the random.
And you did it for the reason of this. You wanted to avoid these big norms, right? So that,
yes, exactly. And we didn't want. Yeah, I mean, it just wouldn't work without variance reduction or like other cleverness.
Right. Right. Yeah. Okay. Does anybody else have any questions?
But maybe the thing I should mention is that this is, at least for the cubic lattice, this is trivial to implement. This is pretty much the same as stochastic quantization.
So let's see. Any more Q&A? I can of course keep asking, but maybe we can just do it private later on.
Becoming like
I could question, question you, not question you, but ask you about this for a very long time.
I mean, people can drop out whenever they want.
Yeah, let's see. But I don't want to steal the time here in case somebody is hesitating to ask and doesn't want to interrupt me or something. So. Okay, then I guess I'll wrap it up, and I thank Dan again for the talk.